we've talked about electric fields and what they are. Now we're going to talk about applications of electric field or specific details that we need to understand electric fields better. So let's say Fred and Francine have a solid metal sphere that has a positive charge. It sits on an insulating stand, so it can't lose that charge to the ground. Fred thinks that if you looked inside this sphere, you would find that the electric field is going to be largest closer to the edge, and then it decreases as you go to the center of the sphere. So he says electric field is largest on the inside edge. Francine thinks the electric field is going to be constant throughout the inside of the conductor. So who is right? Let's look at what happens to an electric field if you're inside a conductor. First, as soon as you put a charge on a conductive sphere, the charges will go into electrostatic equilibrium. So they will spread out as far as possible from each other because the positive charges will repel each other. Well, it's actually the negative charges that move, but overall the net charge becomes spread out. This happens almost instantaneously. As soon as you put a charge on an insulated sphere, the charges quickly spread out. And they're going to spread out so that they're the farthest away from each other as possible on the outside of the conductor. If you looked on the outside of the sphere, you'd see that there is an electric field, and it's perpendicular to the surface moving away. We use this equation for electric field. So as you move further away, as radius increases, your electric field will decrease. So the strength will decrease as the distance from the conductor increases. We can treat a spherical conductor just like a point charge where the center of the sphere is where the point charge is. So we can calculate the electric field outside of the conductor using the basic equation for electric field of a point charge. But inside the conductor, things are going to be a little bit different. Inside the conductor, we said that charges have reached electrostatic equilibrium. That means that they're not moving anymore and they don't have a net force on them. If they had a net force, they would be accelerating. Since they don't have a net force, it means that they are at equilibrium, they're at rest. Now, if they're in equilibrium, that means there must be no net force acting on them. If there's no net force acting on each charge, then there can be no electric field inside a conductor. And we use this relationship between electric field and electric force. We said electric field is the electric force per unit charge. Well, if there's no net force acting on a charge at any point, if that's zero, then that means the electric field must also be zero. So if you go to the center of a conductor, the electric field anywhere inside the conductor is going to be zero because it's going to have no force. Once it's in equilibrium, there will be no electric force in the center. So in terms of Fred and Francine, neither one is right. There's no electric field inside a conductor. Well, technically, Francine was right. She said electric field is constant throughout the sphere, and yes, it was a constant zero throughout the sphere. Fred was wrong. He said it was largest on the inside edge. It is largest on the outside edge, but on the inside, it's all going to be zero. So this is the concept behind what are called Faraday cages, and we'll talk about that in class. This is a cage that is conductive, that has no electric field inside, that a person can be inside a Faraday cage and not feel any electric field, even if there's a very strong charge on the cage itself. All right, the next thing we want to talk about for electric fields is a specific arrangement of charges called an electric dipole. And you can see by the word it's polar and it is di, which means two. Electric dipole is when we have two equal and opposite charges. This is sideways. This is a negative and a positive. They have a separation between them. So there's a negative charge here and a positive charge here. That creates a dipole. A dipole could be inside an atom. Let's say we have an atom right here and we bring a positive charge towards it. that will make the negative charge move towards the positive and the positive charges move away. This atom becomes an electric dipole with a negative charge here, or actually the center of negative charge is here and the center of positive charge is here. So there would be a dipole right here. So an electric dipole is something that we will see in the world around us, so we have to understand how it creates electric fields. Now, electric dipoles also have what's called an electric dipole moment. This is this arrow right here. It's a vector. It points from the negative side of the dipole to the positive side. And that's just something that's defined as this is the direction of the electric dipole moment. How do you remember the direction? How do you remember that it goes from negative to positive? Because with electric fields, we always considered arrows going from positives to negatives, and this is backwards. So the way to think about it is, what would happen to an electric dipole if you put it into a constant electric field? So if you put it into a constant electric field, let's say we have an electric field going upward, the dipole is going to change position to reach an equilibrium position. And when it does reach equilibrium, its electric dipole moment will line up with the electric field. So let's say we start it putting it in sideways. Now overall there are forces, there's a force up and a force down that should be balanced, except that we actually have an axis of rotation. Remember, with rotational motion, you could have balanced forces, but if there's torque, then we will have a rotation. So there's going to be torque on this dipole that's going to cause it to rotate counterclockwise. So it will start to turn. It still has overall torque causing it to rotate, and eventually it reaches this position where it has a force up and a force down. These forces are parallel to the direction of the radius, which means that there's no more torque. This will be in equilibrium, and you'll notice that the electric field is pointing up, and so is the electric dipole moment. So in its equilibrium position, the electric dipole moment will line up with the electric field. That's how you can identify the direction of an electric dipole moment. All right, so let's consider this is also an electric dipole. What kind of electric field does it create around it? Because it's not just a simple point charge. Now we have 2 point charges. So to get an electric field from multiple charges, we're going to add the electric fields from all of the charges together. Now each electric field is a vector, so we're going to be doing a vector sum at each point. So let's look at points A and B. So we're going to use this to find the electric field of a dipole. Let's look at point A. We have our positive and negative charge. At point A, we have an electric field from the positive charge that's moving away. Now you'll notice that this electric field from the positive charge is greater than the electric field from the negative charge. So at this point, we have an electric field from this charge and an electric field from this charge. The positive one is greater because it's closer. So combined, we have a positive charge up and a negative charge down, and our net charge from this dipole is going to be an upward our net electric field from this charge is going to be an upward vector at point A. At point B, from the positive charge, we have an electric field pointing down to the right, and from the negative charge, we have an electric field pointing down and to the left. The distance between this point and the positive charge and this point and the negative charge in the y direction is equal, and in the x direction is also equal. So when we add these two vectors together, we end up with the x components canceling each other and the y components combining. We end up with an electric field that points vertically downward. If you looked at many points around the dipole, this is what your electric field looks like between two equal charges. Overall, we have upward in the vertical axis and upward in the vertical axis below. If you're exactly on the x-axis, we have a downward electric field, and then things move away from the positive charge up here and towards the negative charge down here. This is overall the electric field of an electric dipole. The last thing I want to talk about is a specific type of electric field that we can get from a parallel plate capacitor. We're going to talk about capacitors a lot as we continue in the class, but this is just an introduction of what it is. This is what a capacitor would look like if you did it in an electronics lab. These are actually rolled up layers and layers of capacitors. But if you could look at the simple case, we would have one plate of area A and another plate of area A. They're separated by some distance d. One plate has a charge of negative Q and one plate has a charge of positive Q. So when we create a parallel plate capacitor, what happens to the electric field in between these two plates? What we get is a uniform electric field. Our electric field goes from the positive to the negative, and anywhere between the plates we have exactly the same electric field. This is very useful for certain types of scenarios in physics where we want to have exactly uniform electric field. So let's consider, for example, if we put, now we've actually flipped our electric field for this example. Let's say we put our electron or a negative charge inside the capacitor. Where is it going to have the most stored energy? Where does it take the most energy to hold it in place? Is a negative charge going to be hard to hold up here by the positive plate, somewhere in the middle, or down by the negative plate? Well, the most electric potential energy is beside the negative plate because this negative charge wants to repel from the negative and move towards the positive. Remember that negative charges move opposite of electric fields. So, since the negative charges repel each other, it takes the most energy to hold it here. So we're going to put it right here, but it takes some energy to hold it there. What happens if we stop holding it in place? What is it going to do? Well, it moves where it has an attractive force, which is towards the positive plate. It will accelerate towards the positive plate. So the last thing I want to talk about is how we define an electric field in a parallel plate capacitor. And we have this equation, which is on your equation sheet. It says the electric field inside this is specifically for a capacitor, is equal to the charge on each plate, which is given in coulombs and represented by a capital Q, divided by the area of the plate times epsilon naught. And that's the permittivity constant. That has to do with what is inside the capacitor. And the permittivity constant is going to be, for just a standard capacitor, is going to be this value, which is on your equation sheet also, so you don't need to learn it.